So, for what we're doing today, I have a mystery spinner. A mystery spinner is one where you can't see how it's divided up. Here's your challenge. I want you to predict what the spinner looks like without ever having seen it. Okay, I'm going to spin the spinner and I'm going to announce the result each time. In the space below, keep track of the colors and the number of times each one is spun. So I'll call out what color it is. Make sure you have that color written down if you don't already. And I would just put another tally mark by it to keep track of how many. So your job is to try and figure out what my spinner looks like. All right, let's do this. All right, my first spin is blue. So write down blue, put a tally mark by it. My next spin is also blue. My next spin is also blue. And you're like, is it an all blue spinner? No, it's not an all blue spinner. My fourth spin is blue. This is getting a little ridiculous at this point.
But there's a chance that it's not really 100% blue, but it's still not really blue at the same time.
So I'm not even sure who's talking.
Oh, sorry.
It's all right. I'm sorry. Say it again.
There's a chance, even if it's not 100% blue, there's still a chance that it could be blue at the time.
I suppose. Oh, now it's green. Well, now it's red. And now red again. How many is that so far total? Is that 9? 8? 7? All right. Blue. Red. Red again. How many are we up to? 10. You want to do a couple more? Do you feel like you know what mine looks like?
Not really.
Not yet? Red again. And blue again. All right, we're going to stop there. So what I want you to do is use the data that we have. So how many blues were there? There were 6 blues. And then there was red. How many reds were there?
There were 5 reds.
5 reds. And then
1 green.
1 green. Okay, so see if you can draw what you think the spinner looks like. Based on this evidence, we've spun it how many times total? 12 times total. So how much of it do you think ought to be blue?
Half.
It'd be half, right? 6 out of 12? And then I've got 6 more. So I'm going to divide this up into 6 pieces, which is not particularly easy to do. But I'll try to get it pretty close. So 5 of those 6 would be red. So all of this would be red, and this little bitty one is green. So this is what we got experimentally. Now, does that mean that this is the way my spinner actually looks?
No.
No, because what you get from an experiment may not be the same as what you get or should get theoretically. What do you think, and I want you to think about this before anybody answers. What do you think might help you make a better guess? Don't answer out loud. Don't raise your hand. Just think about it for about 20 seconds. So, Garrett, imagine that's not what we're working on, so please put it away. The thing in your lap is what I'm talking about. All right. Let's see. Who can I pick on? I need to pick on somebody. Rory, what do you think? What might be helpful?
We don't actually know if this is the right one.
Right? We don't know that this is the right one.
Maybe we can do more and it will like it be closer.
Yeah, you're exactly right. If we did more, then it would be more likely to be correct, right? So that's like, I think we talked about this a little bit yesterday. If I flip a coin 4 times, it should theoretically come up to be heads twice and tails twice. But you wouldn't be surprised if it was heads 3 times and tails only once, would you? But if I flipped it 100 times and it came up to be heads 75 times and tails only 25 times, although those are the same percentages, would you be surprised? Yeah. So, what would make a better guess? More spin data. It might also be helpful to know, well, how many sections are there? Because is it possible that I have orange on mine,
Yes.
but it just never spun it because it was so small?
Yes.
Yeah. All right, are you ready to see mine? Oh.
Oh, what?
There's what mine looks like. Now, were we fairly close? Yeah, we got that it was half red, but we thought blue was bigger than that, didn't we? Because green didn't get spun very often. Did we have red was half? Oh, we had that blue was half. Oh, it wasn't as good as I thought it was. We had these backwards because blue got spun a whole bunch. Okay, if I had spun this like 120 times, probably we could have made a pretty accurate one. Okay? All right. So let's find the theoretical probability for each color on the mystery spinner. So we had red, we had blue, and we had green. And we want to find the probability for each one of them. So probability for red,
It's 50%.
so it looks like 50%. What about for blue? All right, I'm going to add something that's going to help you out.
Divisions.
I'm going to show the little subdivisions. How many pieces has this been broken into?
30 is
There's 6 pieces, all equal. Blue is 2 out of those 6 pieces. So that's 2 out of 6, which is 1/3, which is 33.3 repeating percent, right? Oh, and then green was only 1 out of 6. 16.6 repeating? All right. I'm going to change this. Apparently I had orange in this before. Let's do blue. Let's change that to blue, please. So if you spun the spinner 6 times, how many times would you expect it to land on blue? 2 times. And the way you can do that is go, the probability was 2 out of 6 multiplied by 6 is 2. All right, the 6's would cancel. What if I spun it 48 times? Well, that's 2 out of 6 times 48. Let's see, 6 goes into 48 8 times. Times 2 is, we would expect 16. What if we spun it 100 times? We would expect it to be about 33. Because as a percent, it was close to 33%. All right, let's go on to the back of that page. So today we introduced Rachel and Christine, who we will come back to in a later lesson. Rachel and her little sister Christine often argue about who should wash the dishes at home. Rachel suggests that they flip coins to solve their argument. She thinks flipping a coin is fair since heads and tails each have an equal chance of happening. Each one has a probability of 1/2, Rachel says. If the coin shows heads, then I do the dishes. If it shows tails, then you do them. Okay, that makes sense. Is this a fair system? Yeah, assuming it's a fair coin and it's not weighted. So is it a fair? Yes. What's the theoretical probability for heads? The probability of getting heads
50%
is 50% or 1/2, either way you want to think about it. What's the probability for tails? The exact same thing. All right, so Rachel and Christy flip a coin every evening for the first week. Christy has washed the dishes 4 times, and Rachel has washed the dishes 3 times. Christy tells Rachel that the system is not fair because Christy has done the dishes more often than Rachel. Is Christy right, Quentin?
No, because I mean, a week doesn't have 8 days, so.
Well, wait a minute. What do you mean? Why is 8 important?
Because like if it's half and half, she got 4, which is more than yeah, it's more than half or so.
Right. So what are you saying?
If there were 8 days, 50 and 50, it could be 4 and 4.
Okay. So maybe the next day it'll be 4 and 4. So the answer is no. And with 7 days, it's impossible for each of them to have done the dishes the same amount of time, right?
Unless you split the third day.
I suppose. Oh, now the plot thickens. After a second week of coin flipping, Christy has washed the dishes 10 times and Rachel has washed the dishes 4 times. Now Christy is really upset at Rachel because she thinks she has washed the dishes so many times. In light of this new information, do you think the system is fair or not fair? Sam, what do you think?
It could still be fair. Now, of course, the coin might be weighted to land on
Okay.
more, but
So what would you recommend to Christy?
get a new coin, or spin it, or flip it more times, or get a larger set of possibilities.
Okay, so it's probably still fair. What would I say to Christy? I would say be patient. It will work out in the long run. Yes, Quentin.
Just do them every other day. Like make your sister do it one.
Oh, you could do that, but then all the fun math part would be gone.
Yeah, then you don't get mad. And then this whole ring.
Well, if it was a real life situation, yes, that's what they should do.
Yeah, they could. They could do it every other day. All right. So let's move on to another one. We will frequently use a deck of cards to do probabilities. The first year I did this, I found out, to my surprise, that there were many students who had never even looked at a deck of cards before.
Are you serious?
Yeah. I had some angry parents.
That's crazy.
My daughter has never looked at a deck of cards in her life. And I'm like, wow, that's like, I should call CPS on you or something. I mean, everybody should look at a deck of cards at some point. So here's what a deck of playing cards looks like. So it'll help if you know about a standard deck of 52 cards. It has 4 suits. This is clubs. This is spades. This is hearts. And this is diamonds. Each suit has 13 cards numbered 2 through 10, 3 face cards, and an ace. An ace is not a face card. Why not? Because it doesn't have a face on it. Okay? These are called face cards because they have faces on them. So these are all face cards.
There's no joke in this game.
Yeah, standard deck does not include jokers. That's a good question. And yours is not in color, so I'll point out to you that clubs and spades are both black. And hearts and diamonds are both red. So it's also going to be helpful to know that a standard number cube, or a die, has 6 sides. Each side has each side has a different number of dots, 1 through 6. I think pretty much everybody is used to those. So, let's look at the situations below and decide if you can find a theoretical probability for each one. All right, so picking an ace from a standard 52 card deck. So how many aces are there out of that deck? Anybody? There's 4. And how many total are there in a 52 card deck? 52.
Or I believe it would be. I believe it would be 113.
Yeah, it's 1 out of 13. Because if you think about it, each suit has 13 cards and has 1 ace. So it's 1 out of every 13. All right, picking an odd numbered club from a standard 52 card deck. An odd numbered club. So an ace, some people are like, is that 1? Well, does it have a 1 on it? No, so it doesn't count as a 1. So the 3, the 5, the 7, and the 9. That's 4 out of 52. Hey, that's the same. It's 1/13. Here's an interesting one. What is the chance of not rolling a 3 on a standard number cube? How many numbers are not 3?
5.
There's 5. Out of how many total are there?
6.
There's a 6. The chances of a thumbtack landing with its point up or on its side.
I mean, like, wait, that's it's always gonna happen.
We don't know.
I mean, it has.
It's got to land on one or the other, but do each have an equal chance?
No.
Yeah, I think it's actually more likely to land on one than the other. I don't know which. Probably on its side.
Probably.
All right, how about this one? Getting the one red crayon from a set of 8 different color crayons. That's 1 out of 8, right?
Mr. Davis?
Sir.
I didn't quite hear that before. Why would you say it again, please?
I'm sorry,
I
what?
didn't quite hear the explanation for the 4-1. Can you say it again?
Well, if you were to toss a thumbtack up in the air, it's either going to land with the point up or it's going to land on its side.
Yeah.
Are each equally likely?
Theoretically, yes.
I don't think it is. I don't know. But I have no...
We'd have to test that experimentally of flipping it over
Right.
time, so this is theoretical.
Right. So we can't determine it because we don't know if they're both equally likely. All right. So let's talk about modifying the sample space. So if you want to have the best chances of getting a red gumball from a gumball machine, is it better if the machine is full of gumballs or half empty? It's an interesting question. How do the chances of getting an ace in a deck of playing cards change if you have 3 or 4 decks of cards as opposed to only 1 deck? In this lesson, you're going to think about what's called the sample space. The sample space is the collection of all of the possible outcomes. All right, so for this, pretend you've been given a bag containing a set of colored blocks. 1 yellow, 2 red, 4 green, and 5 blue. Further pretend that every student in the room has received a bag that is identical to yours. If you were to reach in the bag and select one block without looking, what's the likelihood that it would be red? Well, how many reds were there?
2.
Out of, how many total blocks are there? 12? So it's 2 out of 12. I'm just going to leave it as 2 out of 12 for now. I'm not going to bother reducing it. What's the probability that it's going to be green?
4 to 12.
4 out of 12. Blue?
5 out of 12.
5 out of 12. Orange?
1, 0.
0. Oh yeah, I almost fell for it. 0 out of 12. Do these answers represent theoretical or experimental probabilities? Theoretical. We did not perform an experiment. All right, so if you were to select one block from the bag 12 times, replacing the block you drew between each selection, how many times would you expect to get a blue block? Yeah, because it was 5/12 is the probability, and I've done it 12 times. What if you repeated the experiment 24 times? It'd be 10, because 5/12 times 24 is going to be 10. Now, imagine that you and another student have combined the blocks from both of your bags into one bag. Do you think the larger sample space will change the likelihood of drawing blocks of different colors? Hang on a second. I'm not looking for answers just yet. Thank you. Answers the questions below to help you find out. How many total blocks are in the bag now?
24.
There were 12 before, so there's 24. How many of each color? Let's see. What were my colors? Yellow, red, green, and blue. So how many yellows are there?
2.
Green? Green was a color, right?
8.
Green would be 8. Was it red and blue?
Yep.
Red?
4.
4, and then blue?
10.
10. Wait a minute. Something's not right. Oh, green's not 4. You guys told me green was 4.
Oh, you said it was 8.
It should be 8. And then blue is 10.
Yeah. Then you said you think, you said, are you sure that's
18, 20, 24. All right. So let's find the theoretical probability for selecting each color. What's the probability of getting a yellow? I'm just going to put Y for yellow to make it a little faster.
It's the same shit. It's 1.
It's 2 out of 24. What does that reduce to?
1 out of 12.
Is that the same as it was?
Yes.
Yeah. What's the probability of getting a green?
Right, 4.
It's 8 out of 24.
1/3.
If we reduce that by a factor of 2, we get 4 out of 12. Was that the same?
Yes.
Yeah. If we reduced it all the way, it reduces to 1/3. The probability of getting a red?
2 out of 12.
4 out of 24,
Which is 1/6.
which is 2 out of 12, which is 1/6. Is that the same as it was?
Yeah.
Yep. And the probability of getting a blue is now 10 out of 24,
Which is 5
which is 5 out
out of 12.
of 12. Has the probability for drawing each colored block changed?
No.
No. Why is this?
Because
Both the total number of blocks and the number of each color doubled. So if you were to make 12 draws from the combined bag, replacing the block between draws, how many times would you expect to draw a blue block? Well, the probability of getting a blue was 5 out of 12, right? And I made 12 draws. I'd expect to get 5. All right. That's it for today.